afternoon, ladies and gentlemen. I'm John.
I'm Haley.
And we're here to talk to you today about concrete. Specifically,
ASR. ASTMC 1260.
1260 and 1567. So 1260 is standard test method for potential alkali reactivity of aggregates, the mortar board method. Or 1567, 1260 or 1567. And 1567 is determining the potential of alkali-silic reactivity of a combination of cementitious materials and aggregates. So, did I say supplementary? Yeah, cementitious. So they mean like supplementary cementitious materials, fly ashes, fumes, slags, blah, blah, blah. So alkali-silica reactivity is when we have alkalis in our binder, our paste content, that reacts with the silica from our coarse and fine aggregate, and it produces this expansive gel between the interfacial zone of the hydrated cement matrix and our granular skeleton, those individual aggregates, coarse or fine. And this expansive gel, well, it grows in this confined space, and it first turns into an immature gel that's very expansive, that has a fiber-like morphology. There's a beautiful soft X-ray morphology paper on ASR gels by Kim Curtis that was done in 1996. Haley will put the link down below. But it really is just a beautiful thing. I did a ASR gel polymerization study using scanning electron microscopy and colloidal silica in my composites through a British standard. I'll put the link for that below. It's absolutely gorgeous. We looked at the ASR gel rosettes, but you get that immature gel, making full circle. We get that immature gel that gets created around the interfacial zone between that coarse and fine aggregate, and then as it dries out, it becomes a mature, more brittle, less expansive, less viscoelastic gel, or like I said, more brittle. And then what happens is as more water and alkalis leach into that unreacted silica from the aggregate, you have that vicious cycle of more immature gel growing, but it gets confined in that zone, that interfacial zone, and that confinement stress overcomes the tensile and shear capacity of the concrete, and eventually you get cracking, and this is what it looks like. Ding! And you can even read about it in our book, The ABCs of ASR, which is a great book for all junior and senior engineers who are just learning or have worked with ASR before. We'll put the link down below. That's it. So, how do we measure it? Haley, I'm going to close this door.
We use these handy-dandy molds to make some mortar bars.
We put some nuggets at the end of these nuggets. Yeah, that's not the right name. Nuggets. We put these nuggets at the end of the mortar bar. It fits into these little slots over here, and we'll do a close-up. Did we do the close?
We're doing it.
We're doing the close-up. So, the close-up. We need one of those.
Here we have.
Okay, don't want to sound like Gollum. So the mortar itself is made out of either, you can use sand, but if you're going to do it by the book, there's a very specific gradation of ground, sieved, and cleaned sizes that you're supposed to use to get this beautiful mortar mix. It's 440 grams total cementitious, 990 grams of your aggregate, and then a 0.47 on your water cementitious ratio. What you're measuring is the impact of the environment on this bar to create a length change. And that length change is measured over, it used to be 14 days and now it's 28 days.
I thought it was like a year.
No. This is the accelerated. See, look.
Oh, okay.
Does it say accelerated?
Yeah.
Accelerated! So it's a 14-day test. Now it's been extended to 28-day. 175 degrees environment. Sodium hydroxide solution that I believe is at a 4.
I think
It's either 4 molarity. 4 molarity. And then you got 3 of these bars. Now, first 24 hours, it's in a tap water bath, but then after that, you take a measurement, and that's your 0 point. And then from there, you're measuring the length change from being in that environment. And the thing with ASR...
We have a video on our length comparometer and our process on that, so check it out, link down below.
Ding!
Sorry.
So, we measure 3 of these, we've averaged them, and we look it over that 14 and 28 days, and we call it good if it's below 0.1% expansion in either 14 and 28 days, depending on who you're working with. And then the idea is how much for this 50-67, how much of that combination of cementitious materials do you have to use to get below that 0.1%? And really, that's all that matters. Okay.
Why is it your favorite test?
I love this test. I love this test. No, I really, really do. It's why do I love this test? It's kind of like why I love concrete. Concrete is a very forgiving material, right? Any schmo can put a concrete mix together, can make a sidewalk, and for the most part, it'll last, right? It'll be structurally sound. Mortars are equally easy to make, right? Very, very easy to make, very easy to use. There really isn't any issue with it. You can make it with a kitchen mixer. So why do I love this test? It's kind of like why I love concrete, because it might be easy at face value to run this test, just like it's easier to make concrete. But when you've got to be good at something, and when you've got to get very high precision, because when we do this test, how
to the 0.000.
1. She's right. 0.0001, and you only have a few seconds to take a measurement when you take it out of the bath. And you have to take a reference or a tear.
Every single sample.
Every single sample. You've got to keep track of your temperatures of everything. And you also have to keep track of the changes between each sample sets from the last measurement. Oh, I'm like getting lightheaded from saying all this stuff. So the reason why I like it is because at face value, it's very easy. And this is just the beginning of it, but when you get into it, it's a very unforgiving test. It requires somebody who is, really loves and appreciates to do it right. Because it's something as simple as, just saying that the tear or the bar is 0.0 all the way, or 0.20, 0.3339 all the way through, it might seem inconsequential, but it makes your data erroneous. Now, what it's used for, another reason why I love it. So that first reason is it's I don't know if we should erase this part out. It's like my wife, unforgiving, right? I mean, that's why I love Whitney. Whitney holds me to, especially with the company, my education, and most importantly with our kids. She holds me to a very high level. And she makes sure, it's 10 out of 10 times, not 9 out of 10 times. And with this test, you have to be, in my opinion, to do it right at that caliber. So that's the first thing. Unforgiving, you have to be good to do it right. We actually went to, worked with the folks at Oregon State University. We paid, thank you again, Professor Eidecker, Jason Eidecker, and your team. They walked us through the test, we sent them samples, they ran tests with us concurrently to make sure we were getting the same data set, and they worked with Whitney on the titration process, which is pretty tough. The other reason why I like this test is, it's relatively simple to do. You get results in a short period of time, less than a month. It doesn't take that much to do it. Yes, you have to make sodium hydroxide, that's salt water. And then you could do some pretty cool tests. We've done replacements or addition with colloidal silica, with carbon nanotubes, alternative supplementary cementitious materials, so many things with this test, even spray-on products. So this really is, it's just such an entertaining test too. You got to pull out samples when they're 175 degrees, you have to use special gloves and special PPE and
I like to think about all the things happening inside this tiny little thing that I can hold in my hands.
And I think that's one of the biggest problems with the test is people often try to take more away from the test than you really can. It's like I once wrote a paper about, and it was I was doing compressive strength tests, and in the paper I started referring to the impact that the colloidal silica had on the molecular kinetics of cement hydration. And my advisor was like, dude.
English.
Well, no. You broke some 4x8 samples, 4-inch diameter by 8-inch tall. It has nothing to do with molecular kinetics. It's compressive strength. You've got a very fancy nutcracker, right? Like, focus on what you're talking about. People will take this test, they'll chop it open, they'll look at, I mean, there's a whole freaking career. It's called, petrographic analysis, where people chop this open, they put it in epoxy, they polish it, and I find it very difficult to use this as a post-mortem, especially when you have to destroy the sample to look at the gel. So I think it is bastardized to a certain degree. I would even argue that using it out to 28 days is a bastardization of it, although we've been known to do it. Where do you think this has a place in the industry?
I think when testing new materials, for sure.
Mm-hmm.
Especially when you might be making an RCA or
Mhm.
something that is susceptible to ASR.
Ooh, are you foreshadowing?
Maybe. Yeah, video coming up on that soon. But I think really just like the comparison of, that's where I would use it the most, anyway.
Well, the question is, so ASR, it's not the primary mode for most concrete to fail. It normally leads to something else. There are other things that are nastier, but ASR increases the crack length, increases the permeability of concrete, and it really shows up in a very beautiful way. Ding! Did we already show it?
Yeah,
I just love showing. No.
He loves making more work for me.
Well, not only that, that's very true, but also the pictures of ASR gel, it has a very specific mathematical pattern. Like the separation between the cracks when you start at a point, when you look at the cracks of ASR,
Angles are the same.
120 degrees apart, similar to the Isle of Man, or the flag from the Isle of Man. And then when you look at the ASR gel itself, it's called an ASR gel rosette, and it's absolutely beautiful and has this wispy-like, fiber-like morphology that it's dependent on, and once you interrupt that fiber-like morphology, it doesn't work anymore. Oh, it's just really fantastic, but the problem with it is it's not realcrete.
Right.
Haley asked the question, is it the 1-year test? That's a 1293 that she's talking about. We're actually using concrete, and you're looking at it in a less aggressive environment, still more aggressive than the real world, but you look at it over, I think it's 18 months, especially if you're using supplementary materials. And, that's more realistic, but, if you're using it for realcrete, who can wait?
Yeah.
The 18 months. Now, there is a huge thing in the huge thing in the industry about which test is better. And being an outsider, what are your thoughts? Is it just this? Is it the 1-year test? Is it putting something on a rock for 30 years?
To me, it would depend on what the purpose is.
Oof. Okay, so let me define the purpose. I'm building a bridge in Canada.
Okay.
Eastern part, the greater Toronto area. I've got to build some 4-story concrete columns for my bridge, and let's say I'm using 150 cubic yards just for the foundation. I want to know, and the job takes off in a year. Like, I need concrete on the ground in a year.
Then we can't do the 18-month one. So that rules that out.
So what would you do, Haley? Not what you can't do, what would you do?
Could I make a non-mortar bar method for the accelerated?
Yeah, it's called the 1293.
Okay, I would probably do the 1293.
But that's the 1-year method, or 18-month method.
No, I want both!
So wait, that's a great point. There are some great tests out there. There's the 1567 and 1260. Those are 14 and 28 day tests. There's a British standard, 7943. That is a 72-hour test. Okay, so there are a bunch of methods out there. I think it's a great idea to use multiple methods, especially if we're not talking about budget. If we have an unlimited budget, I would love to do the BS 7943. It's an ASR gel pad test, that 72-hour test. The mortar bar test, the 1293, and put a block of concrete on a rock at Treat Island. I mean, that's impossible. But the more directions you look at a problem, or from different directions, you get a better idea of what it's doing to your materials, or what your materials are doing to the system to create the environment for this chemical and then physical attack to occur. And by looking at it from different avenues, from different chemical environments and heat environments, you get a better idea of what you have to do to make it stronger and last longer.
Well, and you can't really just look at one aspect of it. Like the cement, or the aggregate, in my opinion, in Canada would have more of an impact on ASR than the cement, right?
I don't know. Yes. Yeah, but I think you said it earlier, it just depends.
Right.
Because we're not only, you're right, I focused on Canada, right? So yes, if you make a great point, what I would do is literature review first.
Right.
What has been done. If we're going down the direction of what is the best test to use, maybe it is focusing on, okay, what is our problem here? Is it the cement or is it the aggregate? And if it is the cement, what do we have to do to our cement? Because using a Class F fly ash, sometimes brings more alkalis than just using that cement. So what is really the best approach? And I think you're right, it all depends.
Case by case.
Case by case. But relying, something else you said about sole sourcing one test on your answer, I don't know if that is ever a good idea.
It would make me so uncomfortable.
I will say that that is a part of most DOTs,
Really.
that there is one test for most decision-making things. Yeah.
It's hard.
It
Well,
is what it is.
Positivity Tuesday on a Monday.
On a Monday.
Thanks for watching. Don't forget to like and subscribe. Ding that bell for notifications. Go Concrete!
You didn't let me say anything.
So sorry.
Are you?